All right, so today we're going to talk more about the definite integral, and we're going to try and move away from approximating techniques. We know that the definite integral is really describing an area that's under a curve. We call it bounded between a curve and the x-axis. So if we wanted to draw it, it might look something like this. Here's our graph, and maybe we have our curve. Let's see, I'll try and draw my regular function that I look at here. This is our function f of x, and we'll look at some points, maybe an x value here. There's a, there's b, and we went ahead and said this area looks like this, and we can shade in this area under our curve. So this is our area that we're talking about when we talk about this definite integral. What we really mean, though, is a signed area, and this only comes up a little bit, but if we had, for instance, our function that, let me get rid of this and we'll draw a different function, that maybe did something like this, and we talked about an area from maybe here to here. Now, when we look at our area, part of it is above the x-axis, and part of it is below. So all this area here is a positive area. But this area under here, underneath the x-axis, all becomes negative. So we can get some weird things where, like, if this area here, this positive area and this negative area are the same size, then this integral can actually be 0 because the positive and negative can cancel out. We can end up with negative areas and all this kind of stuff. So that's what we really mean when we talk about area under a curve. We're talking about like a signed area, or sometimes people will call it a net area, because we'll just talk about all these positive areas and all these negative areas added up. Anyways, what we want to do is link this to our indefinite integrals. We've been talking about area. We've been talking about ways to approximate them using some rectangles, and we want to connect these to our indefinite integrals, which really are just antiderivatives. So we want to figure out a way to connect these definite integrals, to antiderivatives. And this is the fundamental theorem of calculus. Here, this definite integral from an x value of a to b is just the antiderivative of b minus the antiderivative of a. So we do this one first and this one second. And we're just plugging these things in to our antiderivative function. Now, you'll notice in this case, there's no plus c or anything like that. You could think of it really like this. The antiderivative of b plus c minus the antiderivative of a plus c, but you'll notice the c's will cancel out. You're going to have a constant minus that same constant, no matter which of your specific antiderivative functions you pick. So depending on whatever constant you pick, it's going to be the same for both of these, because these are the same antiderivative functions. They're any of the antiderivatives from that family of antiderivatives. So this ends up being actually a really easy thing to do if we know how to find antiderivatives. There's really only one more step that we're going to do, and that's just plugging in values. We're going to plug in the top number first, plug in the bottom number second, and subtract our answers. So if we wanted to find this area, first what we need to do is find an antiderivative. So we'll say that this is really going to be, our power rule is x cubed over 3 minus 5x, and normally we'd say plus c, but I'm going to do something a bit different now. I'm going to use this vertical bar, which means evaluated from 0 to 2. So we're going to evaluate this function from 0 to 2, which means I'm going to plug in 2 first, plug in this one here second, and then subtract my 2 answers. So this ends up being 2 cubed over 3 minus 5 times 2 minus whatever happens when I put in 0 into this antiderivative. 2 cubed is 8, so we have 8/3 minus 10 minus 0 here. So 8/3 minus 10 is really 8/3 minus 30/3, so this is negative 22/3. This is the area that we're actually looking at underneath this parabola here from 0 to 2. You'll notice it's a negative area, and that's because when we draw our parabola, it ends up looking something like this, and we're looking at the area from here to here. So we're looking at maybe, I don't know, maybe this area that's shaded in right at this spot. Now this isn't a perfect drawing, but we can see that this is below the x-axis. That's why we've got this negative sign. Similarly, we can have it set up a little bit differently where it just says, okay, find the area under this curve from whatever x value to x value. So really, if we translate this to integrals, we're looking at the integral from 2 to 4 of 2e to the x minus the square root of x dx. I'm going to rewrite this right away so it's easier to find antiderivatives. I'll say the integral from 2 to 4 of 2e to the x minus x to the half. And now I can just find antiderivatives. The antiderivative of 2e to the x is still 2e to the x. The antiderivative of x to the half is x to the 3 halves over 3 halves. And then instead of saying plus c, I'm going to use that vertical bar that says I'm going to take this antiderivative and evaluate it from 2 to 4. I'll maybe simplify it a little bit. This is 2e to the x minus 2x to the 3 halves over 3. And I'll evaluate this from 2 to 4. Now I'm just changing this denominator. All right, so now I can start plugging things in. I'll plug in 4 first. 2e to the 4 minus 2 times 4 to the 3 halves over 3 minus 2e squared minus 2 times 2 to the 3 halves over 3. And now I just need to figure out what these things actually are, what these values are, and I can do that in a second. So I'm going to grab my calculator, pull these up, and we'll get some sort of an approximation for a decimal point here. All right, so I just plugged this in to get an approximate. I'm going to 2 decimal points because that's good enough. Here I've got 103.86. That's this first set of parentheses. And I'm going to subtract 12.89. That's the second set of parentheses. And that gives me approximately 90.97. That's the size of the area under this curve from an x value of 2 to 4. We can call that just square units. We can eventually put some context on this, and then we could have some specific units for all that stuff. But right now, that's good enough. So it ends up being pretty easy. Just go ahead and evaluate your antiderivatives at certain points. Make sure that you keep track of your signs. I like to evaluate each of these set of parentheses individually like this, so I can just subtract your answers. But other than that, things should go pretty easily.